Okay, in the previous lecture, we are discussing how to interface the output devices with the microprocessor. So we have seen there that for interfacing the output device, we use the instruction out, and it is having an 8-bit port address, right? So once that address is placed on your address bus, that 8-bit address, a unique address, so you get a unique pulse here, which is called as input-output address pulse. And this pulse in combination with the input output write signal, so you combine them using a NOR gate, this is a logic low pulse, to generate a logic high pulse, and this logic high pulse is basically used to enable a latch. So this is the data bus D0 to D7, and to this we connect the peripherals. Okay, so you may connect some LED displays here and so on. Okay, this is what we discussed, how to interface the output devices, and then we have seen how we can interface a 7-segment display with this. Okay, and this address decoding circuit, you can simply use simple logic gates like NAND gate. Otherwise you can use a decoder circuit here also to decode the address. Okay, now in the same way you can interface an input device like DIP switches. So DIP switches, dual inline package switches, they are generally used in your PCBs and in various control applications. But the concept is same. Of course, in this case, the instruction that we use is now in with along with the 8-bit port address, that is port 80H. Okay. So once this instruction is executed, the processor will send the data from it will get the data from an output port which is identified by address, that is 80H, and that data should come inside the accumulator in the microprocessor. Okay, so again, now in place of the latch you must have some output, you can say a tri-state buffer, and that buffer must be enabled when this unique address is placed on the address bus, and along with that when the processor assets the signal input output read signal. Okay, so in place of write operation, now you have read operation. Okay, so if you have a simple decoding circuit using a NAND gate, let us suppose we connect all the address lines A0 to A7 to a NAND gate. So this NAND gate will generate a input output address pulse, logic low pulse, only if all the inputs are at logic 1. Okay, it means the device address, the port address that you have set in this case is your FFH. Okay, so you can modify the hardware here and you can change this address to anywhere from 00 to FF. Okay, so once this address FF is placed on the address bus, this decoding circuit will generate a active low pulse, which is called as input output address pulse. Now this pulse has to be combined with another pulse, that is now input output rate pulse, which is generated by the microprocessor. Okay, because see, once the processor executes this instruction, which is again a 2-byte instruction, so first is your opcode, the second is the 8-bit port address. So once the processor fetches the opcode and decodes it, it comes to know that it has to get some data from the input port. Okay, so then the next memory location, that port address will be stored. So then this processor will place that port address on the address bus, and at the same time, in the T2 of your machine cycle M3, the processor will generate a control signal input output rate. Now once this processor assets this signal input output rate, these two signals are again combined using a NOR gate to generate the active high pulse. Now this active high pulse will be used to enable a tri-state buffer. In the initial case for output, it was used to enable a latch. Okay, now this will enable a buffer, a tri-state buffer. Okay, so the input of this buffer is now connected to your DIP switches, and the output of this buffer is connected to your data bus D0 to D7. Okay, so the data from the data bus will go inside the microprocessor and it will come in the accumulator. Okay, so at the input you have some switches, so the switches can be placed accordingly. You can keep it on or off, and accordingly the signal at the input can be either it is logic 0 or logic 1. Okay, so DIP switches, you can have 8 DIP switches here. So this is connected to plus 5 volt. Similarly, this is the second is also connected to plus 5 volt. The third is also connected to plus 5 volt using a current limiting resistors, and all the switches like so on. And at the second, and we have a ground terminal here. Okay, so then you have switches here. So this switch can be on or off. Okay, when the switch is in the off position, it is not connected. This data line is connected, input line is connected to plus 5 volt. It means you will have a logic 1 here. Okay, if you turn on or close any switch, particular switch suppose here, so it is connected now to ground, so you will get logic 0 here. Okay, so suppose in this configuration only this switch position is closed, so at this input you have logic 0, so another pins you will have logic 1. Okay, so this buffer will basically read the position of these switches. Okay, accordingly whatever is the data on these switches, logic 0 or logic 1, that will come on the data bus once this buffer is enabled. So inside this we have a tri-state buffer. Okay, so tri-state buffer, you know what is a tri-state buffer. It has 3 states: logic 0, logic 1, or high impedance state. So when it is in the high, when it is not enabled, it is in basically in the high impedance state, means it is disconnected from the system. Okay, so when it is enabled, so the data from the input comes at the output. Okay, so it is enabled only when a logic high pulse comes at the output of this gate G2. Okay, and this logic high pulse will come only when you place a unique address, that is FFH, on the address bus, and when the microprocessor sets this signal input output rate, then only this buffer will get enabled. And once this buffer will get enabled, so at that time whatever will be the switch position, so that data will come on the data bus and it will go inside the microprocessor. Okay, so this is how you can use or you can interface the input devices like DIP switch with the microprocessor. Okay, so in place of this, you can use a decoder circuit also for decoding, like we have done in this interfacing output devices. So if you use a decoder circuit, 3-state decoder, so you have 3 inputs for address, then you know there are 3 enabled pins. 2 are active low, 1 is active high, E1, E2 and E3. So this is, now you have 8 address bits, so you have A0, A1, A2, they are connected to this input to the decoder, and the rest of the chips they are used for enabling this chip. Okay, so you can use any combination. So you have 8 bits, A7 to A0. Now A0, A1 and A2, they are used for decoding the address, and A3 to A7 they are used for chip select. Okay, so for selecting this chip you can have different combinations. Suppose you connect directly A3 with this enable pin E3, and rest of the pins, rest of the 4 pins, that is A4 to A7, you connect them with a NAND gate, and the output of the NAND gate is connected to E2 as well as E1 pin of this decoder. Okay, so this chip will be enabled when your A3 is 1, and at the same time when A4 to A7 all these 4 bits are 1 1 1, because only then it will produce a logic 0 output here. So this logic 0 output will enable your decoder. Okay, now the output address bus, now we have 8 outputs here, so you can use any output to generate this input output address bus. According to that you have to place a address here. Okay, so suppose if I use if I connect O4 of this decoder with this, combine this with input output read signal to generate the chip select signal. So this will give you active high signal, which is called as input output select signal pulse. Okay, so what should be the address on this to generate this active low pulse set output of this? Since I am connecting O4 of the decoder, it means the combination of the input bits on this should be 0 0 1 1 2 4. Okay, so if you connect all 5 of this, your address will be different. It will be in the case 1 0 1 and so on. And these 5 bits, how you fix them, that depends upon this external hardware that you used. So A3 I am connecting directly with this, it will become 1. And these A4 to A7, since they are connected with a NAND gate, so in order to generate electric low pulse, all these must be at logic 1. So this gives me the port address. Okay, so it is now F, and this is 124 into 48. So 1248, it becomes 12. So 12 in hexadecimal is you have A, B, C, D, E. So 10, 11, 12. So C is your 12. So it becomes FC. So using this circuit, I fix my input port address to FC. Okay. So now this is connected to your enable pin of the buffer. So input you have DIP switches, and output of the buffer will be connected to your data bus. Okay, so through this data bus, the data will come inside the microprocessor depending upon the position of the switches that you connect here. Okay. Now say if you use a decoding circuit like this, since you have 8 outputs, okay, it means you can interface now 8 input output devices using a single decoder, isn't it? If suppose I connect O7 of this decoder to generate another input output address pulse, and that is used for interfacing an input output device, not input device, in combination with input output write signal. So this will be connected in that case to the latch to enable this latch, and the input to this latch is the data bus, and output of latch is connected to your peripheral devices like LED or 7-segment display. Okay, now what should be, now this is my input port. Okay, and I have fixed the address of the input port to FC. It means whenever I want to get some data from this device, the processor has to execute an instruction in FC. So whenever the processor will execute this instruction, the data from this port will come inside the processor into the accumulator. Now since I am using the same decoder for interfacing output device or the output port here, so now for the output, this, since I am connecting O7, it means this pin will go low when you place a bit combination on this, that is 1 to 4, 1 1 1, 1 2 4 7. Okay, and the rest of the chip select pins, they are same, they are all 1 1 1. Okay, it means what should be the address for this port is now FFH. Okay, so if you place FFH on the address bus and the processor resets this input output write signal, so data from the accumulator will go on this latch, and from this latch to the output peripheral devices. So if the processor executes this instruction out FFH, so whatever is in the data in the accumulator, so that data will be placed on this output port. Okay, because the address for now this is FF. Okay. So simultaneously, you can interface many input-output devices using a single decoder. Okay. So you may have one port to which the IP switches are connected, another port to which the LEDs are connected. So if you want to see the status of whether a switch is on or off, so you can simply write instruction from this now in FC and out FF. So what this instruction will do, it will fetch the data from the input port with address FC, and whatever is the position of the switches or whatever signal you are getting from this input port, that will be displayed on the output port with the address FF. Okay, so this is how you can interface input-output devices with the microprocessor. There is one more method of interfacing which is called as memory mapped input-output. Interfacing. See what we have done till now, we are using two instructions for interfacing in and out. Okay, and both of these instructions they require 8-bit port address. Okay, so how you assign a port address to a particular device, that now it depends upon the decoding circuit, right? In the input-output memory mapped input-output interfacing, we use a 16-bit address in place of 8-bit address. Okay, the ports are identified using a 16-bit address, and the data is transferred between the memory and between the processor and this I/O devices using memory-related instructions, not in-out instructions. Okay, the concept is, suppose you have an instruction in the microprocessor for load and store. You have one instruction LDA, suppose 2050H. Okay, this instruction is to load accumulator with the contents of memory location whose address is 2050H. It means you have some memory here, and suppose the address for this memory location is 2050H, and if there is some data at this location, suppose we have 72H, 8-bit data. So once the processor executes this instruction LDA 2050H, so whatever is the data at this memory location 2050H, that data will be loaded in the accumulator. This is what is load accumulator. Similarly, you have one instruction for store accumulator. So suppose I write 2080H. So this is used to transfer the contents of accumulator into a memory location whose address is 2080H. So whatever is the data in your register A, so after the execution of this instruction, the data from the accumulator will be placed at a memory location having address 2080. Okay, and if you execute this instruction load accumulator, so the data from the memory location will go into the accumulator after the execution of this instruction. These are load and store instructions. These are called as memory related instructions. But the same instructions, they are used by the microprocessor for transferring the data between the processor and the I/O devices. Okay, and what is the catch here? What is the concept here? That okay, once the processor suppose executes instruction load accumulator with this address, so in place of using 2050 address as a memory location, this should be address for a I/O device. That is what is memory mapped input output. Okay, so you are using memory related instructions, but the processor says that it is not basically communicating with the memory, although it is using the instruction for memories related to memories, but it is not communicating with the memory. The address which has to be used for memory, now that address is basically assigned to a I/O device. Okay, it means you have any output port or input port Now that input port is identified by a 16-bit address, that is 2050H. Okay. So when the processor executes LDA 2050H instruction, it will now load the contents from this output port, not the memory location. The output port which has the address 205H, so that should come from this memory into this IO device into the accumulator. Okay. Similarly, you have a output port or which is designed using some address 2080H. Okay. So when the processor executes STA this instruction, it will store the contents of accumulator not into this memory whose address is 2080H, but it will store the contents of accumulator to a port. The address for that is 2080H. It means you have 64 kilobytes of memory map. So this is my memory. Okay, of course. So for some of the memory that has to be reserved for data transfer between the memory and this processor. So some memory now you have to reserve for I/O related operations if you are using a memory mapped input output interfacing. Okay, because see, if you execute this instruction, so it may be possible, it means there is some decoding circuit and that decoding circuit should enable a input port which is specified by this address. So 2050 in that case should not be used as a memory location. Okay, otherwise there will be a conflict, right? So you need to keep some separate memory for IO related instructions and a separate memory for your memory related operations. Okay, now how you assign a 16-bit address to this port, that again depends upon this decoding circuit that we just explained. But in place of 18-bit address, now you have a 16-bit address. So that 16-bit address has to be decoded by the decoder. Okay, and in place of using this IO input output read and input output write signals, since the processor is using memory related instructions, it has to use input output, not input output, the memory read and memory write instructions. Memory read and memory write. Okay, the processor basically knows that it is going to get some data from the memory, but it is not memory. At that location you have connected a port. Okay, similarly the processor understands that okay, once the signal goes low, the processor understands that it has to write some data into the memory. Okay, but the address which we have used, no, that is not basically for a memory, it is basically for a output port. Okay, so this is what is memory related input output instructions. So I will show you. See, we have used here is instruction. We use again a decoder here. Okay, so 16, all the 16 address lines now they are used, and we will use the same decoder for interfacing with the input port and a output port. First, let us see what is the input output port address that we are using. So you have 3-state decoder, so 3 lines A0, A1, A2 they are used for this input decoder. Rest of these they are used for chip select. Okay, rest of your 13 lines they are used for chip select. So A3 is directly connected to this pin, which is logic 1. It means it must be set at logic 1. Similarly, A2 and E1, these are enable pins, they must be at logic 0. So these 4 pins, they are connected through a NAND gate to this enable pin, and the rest of these 8 pins, they are connected through another NAND gate to this pins. It means in order to activate these 2 pins, to generate active low pulse on these 2 pins, all these pins must be at logic 1. Okay, so your A3, A4, A5 up to A15, all these bits they are at logic 1 in order to enable this chip. They are used for chip select only. Okay, now depending upon which output is used for generating this input output address pulse, that will define your port address. Okay, like suppose O0 of this decoder is used for output port because it is related to memory write. Okay, it means I must place 000 on these three pins, then only this will give me a active low pulse. And this active low pulse, now in combination with this memory write signal, when they are combined using the NOR gate, you will get the active high pulse here, which is a chip select pulse. And now that chip select pulse is connected to the latch. Okay, so it will enable this octal latch. The input to this is connected to the data bus, and the output is connected to the various devices using solid state relays. Okay, so the address for this latch is now so you have 16 lines starting from A0, A1, A2, A3 up to A15. All the address lines are now used, 16-bit address lines. Okay, so A3 is set to 1, A4 is set to 1, all these pins they are set to 1. Okay, so A3, A4, A5 all are set to 1 because that is how this chip select logic is designed. And in order to generate a logic 0 pulse here, what I have said that these must be kept at 000. So when this 16-bit address is placed on the address bus, okay, so this decoder will generate active low output here. Okay, and once this decoder generates active low output here, and when this processor sends a memory write signal, okay, so this device gets selected. Okay, so the address for this now becomes FFF8. So this is 8, so rest all are FFFF. It means whenever the processor places this FF8 address on the address bus and it sends the control signal memory write, so instead of selecting a memory, the processor is basically selecting a output latch to which some output devices are connected. Okay, similarly we have used O1, the second output of the decoder, for interfacing an input device, that is DIP switches. Okay, so this will be activated when you place the data here 001. Okay, when you get 001, rest are 111. When you place 001 here, this will be high, this is low, this O0 will be high in that case. Okay, again when the processor sets the signal memory rate, so this will generate active high pulse here. Okay, so in this case, since we have used here that it is active low output, so it is connected by another inverter here so that it generates the active low output. Okay, see what we have done till now, we have used this circuit for interfacing NOR gate. Okay, and we have seen that okay, if this is low, this will generate a high pulse. So this high pulse was generated with the enable pin of the latch. Okay, now if the enable pin of the latch or the buffer, if it is active low pin, it means it must generate a active low signal. So in that case, you have to use another inverter here, NOT gate. This is what is basically done here. Okay, and then it will generate active low pulse. So because this is active low pin, the output enable pin. Okay, so just for this become now FFF.